so far, what did we discuss? We discussed the reflection by mirrors. How plane mirror reflects light and how the curved mirrors reflect light. What is reflection? The light that is incident on a reflective surface bounces back into the same medium. So, there we consider only one medium. Now, look at this picture. Here there is a pencil that is kept inside a glass of water. So, there, if we take the glass of water, this is one, this is water, and above water, what is there? There is air. So, this is one medium, this is another medium. And we have a pencil inside the medium, this is the pencil. So, the light rays from this part of the pencil, they are going to travel through water. Then they have to enter the second medium, that is air. So, when this happens, we expect the light rays to go in that direction. But that doesn't happen. The path deviates. So, because of that, the path deviates. So, here, the bending of light rays upon entering one medium from another medium is known as refraction of light. So, here there is one medium water, the other medium air. When light travels from one medium into the other, it doesn't go in the same path, it undergoes bending. Bending can be either towards this side or towards the other side, depending on the two media. We will discuss that in a while. So, as you can see, there are two mediums or two media, and light is traveling from one media to another, and then the light undergoes bending. What is the reason? What are light rays? You all know that they are electromagnetic waves. What is the speed of light? We have discussed that the speed of light is 3 into 10 to the power of 8 meters per second in vacuum. But what happens to the speed when it enters a medium? The speed changes. Why? Because the density of the medium is different. So, through different medium, but they have to be transparent medium that allows the light to go through, the speed of light changes. So, here, when the ray is coming from water, there is a certain speed, and when it enters the air, there is another speed. So, because of that, you can see the object as broken. The pencil looks broken at point Y. That is when a person is looking from this side. So, if you look from the top, you don't see a difference. But if you look at an angle, you hold the glass like this, you put a pen into that or a pencil, and if you look like this, you will see the part that is inside water will look broader than the real pencil. And also you see it as broken or like two pencils attached together. So, that is the result of refraction of light. And that happens because the light bends when it enters one medium from another medium. Now, we will see how this takes place in detail. And before I go to that, can you think of other examples? Where have you observed this? Say we look at the thermometer, the mercury thermometer. The thermometer rises up and down through a very thin tube. A glass tube, but it's very thin, a capillary tube. But when you rotate the thermometer, at one point you can see the line as a broader line. That is possible because of refraction of light. Then you put something into water. You look from the side. Although it's a little below, it looks at a different position. It looks as if the object is slightly above. The same thing for swimming pools or any place where you have water, a water body. You just look into it at an angle. It looks as if the water is shallow. But in reality, the water will be more deeper. What is the reason? The reason is refraction of light. Say you keep your water bottle. You have a transparent water bottle, colorless transparent plastic bottle with water. You can hold your book on one side, hold the water bottle, or just place the water bottle on the table with water. Hold the book from the other side and you look from the opposite side. What will you see? You can see the letters looking larger. The same way, take a glass cube, place it on your textbook and look at the letters through it from an angle. You can see that the letters look larger. All this is possible, or all these are observed in that manner because of refraction of light. So now we will consider another example to understand how this refraction takes place. Slightly raised appearance of an object at the bottom of a vessel of water. So again, this is what I explained. Now we will see how that happens. So let's say we have a vessel containing water and this has to be a transparent vessel. And here, there is an object at the bottom. The object has to be inside water. So this is water. And here this is a transparent glass. And you are looking from this side at an angle. If you look straight through it or look straight into water, you will see the coin as it is. So this is a coin or a small object. But if you look from this side, the coin will be seen at a different position. That is because, now say we have the light rays coming from the coin. It is an incident ray. And here, what is this? There is a normal line. And this point where you have water and top, here we have air. So this is the water-air interface. This is the interface. The point where the two mediums meet. And at that interface, at the point of incidence, we can draw a normal line. Although we expect the ray to travel in the same path, you all know it doesn't happen. So what happens there? The light ray bends. And there is a way. Now here, when light goes from water into air, it bends away from the normal. So this particular ray goes in a direction like that. It was supposed to go this way. It is bent there. So that is the refracted ray. So students, here you can see I have drawn one ray that is coming from the coin. To get the image of the coin, how many rays do we need? We need at least 2 rays. So from here, if I draw the second ray, again that also comes to the interface, and at that point, if we draw the normal line, from this normal line, the ray will refract. So it will bend. Here you can see it has to go this way, but it goes in a different path. So that is the bending of light. So then what we have to do is, I have to show the direction of the rays, the incident ray and the ray that has refracted at the interface. Now to get the image, we have to extrapolate the 2 rays. So to do that, I will need the ruler. So we have to place the ruler in position with both the rays. So first ray that I drew, this one, and I will have to use broken lines because I am going to draw the extrapolated ray, or I am going to just draw the imaginary ray. So here it will be the extrapolated ray. The same way we have to draw for this one as well. Right. So now if we draw the second ray, that has to be also in line with the first one. Here you can see the object will be seen somewhere here. Actually, it's this part of the object that's going to be seen there. So if the real coin is here, it looks as if it's raised. If I draw it like that, it looks as if it's raised up. So the depth at which the real coin is known as the real depth. So from the interface to this part is the real depth. And where you see the coin is known as the apparent depth. If I write that here, so this is the, I will mark the point from here to here, this is the real depth. And this distance where you see the coin is called the apparent depth. Apparent, you can remember it as the depth at which the object appears to be. Really, it's at this depth, but it appears to be somewhere here, slightly raised from the position. So this is due to refraction of light. So as I told you all before, students, there are many instances where we observe this. Any water body, I told you all, the real depth of the water body will be greater than the depth that we see. So that is why they tell you to think before you leap into the water. Okay, now with that I will move on to this. A ray of light traveling in one medium bends upon entering a second medium as described above only if the rays arrive from a direction other than at a 90 degrees angle on the surface separating the two media. So again here, if this is the interface, if the ray is coming perpendicular, then of course this angle will be 90 degrees. So the ray that is incident perpendicular to the interface will be reflected back like this. There will be no bending of the light. So, if this was water and this is air, still the ray will go in the same path. It will not bend. But if it comes at an angle, now say this is the interface, the ray comes at an angle. So, there we draw the normal, and again here this is water and this is air. So, only at this point there is bending. So, here the light bends this way. What we saw before was different from what we see here. Earlier, the light rays came from water into air. There you saw the angle between the normal and the incident ray was a little smaller. The ray bent away from the normal. But here, the light ray coming from air bends towards the normal. So, that depends on the two media. Reason for the refraction is the difference in the speeds of light from one medium to another. So, here it depends on the speed of light. So, as I discussed before, the speed of light in vacuum is 3 into 10 to the power of 8. But when it enters a medium, the speed slightly decreases. We will discuss that in a while. So, here the speed of light is 3 into 10 to the power of 8 meters per second. When light enters another medium from a vacuum, the speed reduces to a lower value. So, here you can see the speed reduces to a lower value when it enters another medium. That is what causes this refraction of light. With that, we will move on to here. Here in this table, you can see the speed of light in different media. A medium with a lower speed of light compared to another medium is called a denser medium. The medium with the higher speed of light is called a rare medium. So, two new terms. Earlier I told you all, because the density of the medium are different, that you know, air is less denser than water. Water is less denser than glass. Why? They are in different states, the gas, liquid and solid. So, there it is the density. Because of this difference, there is a difference in the speed of light. And if the light travels faster through a medium, we call it a rare medium. So, here you can see a medium with a lower speed of light is known as the denser medium. And the one with the higher speed of light is called the rare medium. Now look at the table. The medium is given and speed, here you can see it's given in kilometers per second. All this time we have been using the unit meters per second. So, if we take the speed of light in vacuum, we said it's 3 into 10 to the power of 8 meters per second. If we convert this to kilometers, we have to divide it by 1000. What is that equal to? 3 into 10 to the power of 5 kilometers per second. Here you can see. In air, the speed of light is 300,000. That is 3 into 10 to the power of 5. 300,000 kilometers per second. So, in air and vacuum, it's almost the same value. The speed is the same value. But if you take water, the speed is 225,000. So, that's less. In glass, 197,000. So, as I told you all, gas, liquid and solid. There you can see the difference in speed. So, if we take two substances, now let's say we will consider the two medium. We will say this is water and this is air. Now you can see the speed of light in air is 300,000 kilometers per second, whereas speed of light in water is 225,000 meters per second. So, light travels faster in air. Then we call that as the rare medium. This is the rare medium. And water is the denser medium. We'll take another example. We have an interface there. I will draw another interface as well so that it's easy for us to compare. So, we have the normal line. I am drawing it so that I can easily show you all the way the rays refract. So, here let's take this as the water medium and I will take the other medium as glass. Now, compare the speed. In water, it's 225,000. In glass, it's 197,000. Now think which is the rare medium and what is the denser medium. The light rays are faster in water. So, that is the rare medium. So, here water is the rare medium, glass is the denser medium. Now, can you see? Here water was the denser medium because it was with air. But here we have glass and water. Water is the rare medium. So, the rare medium and the denser medium depends on what are in contact. It depends on the two media that are in contact with each other. Let's take another example. Perspex. Perspex is also a certain material. It's similar to glass but it's different from the normal glass that we use. You all know normal glass is made from silica. But Perspex is another type of glass that is also a transparent medium. It allows light to pass through. So, this has a speed of light in Perspex is 201,000. Whereas diamond, it is 124,000. Let's say we use diamonds. It's very costly. You have learnt about diamonds when we discuss carbon. Diamond is an allotrope of carbon. And why is it very costly and precious? Because of the high refractive index. You can remember that. So, that is what happens here. Let's say we have air and diamond. Now, here we have the air medium and we have the diamond here. And the speed of light in diamond is very much less when compared to speed of light in air. So, obviously there will be refraction or bending of light. And here what is the rare medium? That is going to be air. Air is the rare medium and diamond is the denser medium. So, in all these, when light travels from one medium to another medium, it will undergo bending. Let's say I take a light ray coming from air going into water. When it goes from a rare medium into a denser medium, it bends towards the normal. So here we have to show the arrows. And this is the incident ray. This is the refracted ray. We'll take this example, going from glass into water. Here students, you have to be careful. You have to understand from what medium to what medium the light is traveling. You all have to look at the arrowheads carefully. Here, light rays travel from air into water. Now I'll take another example. The light rays are going to travel from glass into water. So there they will bend away from the normal. So from this, what can you see? When light enters from a rare medium into a denser medium, it bends towards the normal. And when it goes from a denser medium into a rare medium, it bends away from the normal. So what will happen if it goes from air into diamond? It will bend towards the normal. From diamond into air, it will bend away from the normal. So that is how refraction of light takes place. Now I will move on to this activity where we observe how light refraction through a block of glass takes place. The required materials. We need a block of glass. We need head pins. Then we need a board to keep the paper on the board and so that you can put the pins easily. It shouldn't be a very rough, strong surface, then it's difficult to put the pins. If it has a spongy also, then it's difficult to draw the rays. But if it's somewhat soft wood, then it's easy for us to put the pins. Even you can use a piece of regiform, styrofoam. Like a board of styrofoam can be used for this purpose. So we need a board. And here we need white paper. So this is what we are going to do. We need to place the board first on a table, a horizontal surface. On that we place the white paper. We make sure that the white paper doesn't move around. So maybe we can put board pins and make sure that the paper is in place. Then what we can do is we can place the glass cube on the paper. And what I would do is I would first draw the outline of the block of glass. Then first remove the glass and draw a ray at an angle. At a certain angle, you draw a ray, a straight line. And then again place the block of glass on the piece of paper, on the white paper. And after that, we put 2 pins on the ray that we have drawn. That is to indicate the ray again. Thereafter, what we will do is, now we have the white paper here. The block of glass is here. And I have drawn the ray. Let's say I will put the 2 pins there. Then what we do is we look from this side. You have to look from this side. That is, you have to look at these 2 pins from an angle from this side. And then put another 2 pins on this side of the block that is in line with these 2 pins. That is the activity. So the method is place a piece of white paper on a drawing board. So drawing board is also something that we can use so that you can put the pins and place a block of glass on it. Next, mark the edges of the block of glass with a pencil. Mark the position of the block of glass. Now place one pin vertically at a short distance away from the surface and another pin in contact with the surface. So this is what I told you all. You can draw the ray and put the pins as well. Next, view the pins through the surface on the other side and place a pin in contact with the surface so as to be collinear with the pins placed before. So remember this term, what I said as it has to be in line with the pins you put before. So that is what we mean by collinear. Thereafter, place another pin at some distance away from the surface so that all 4 pins appear to lie on the same line. That is very important, where you place the pins. Now, remove the block of glass and the pins and draw lines connecting the points where the pins were placed. Draw the normal lines to the surface. That is to complete the ray diagram. So again, this is an activity to observe how refraction of light takes place. What are the 2 medium here? One is glass, the block of glass, and around the glass what do we have? There is air. What is the rare medium? That is air. And what is the denser medium? That's going to be glass. So we will see how refraction happens here. Let us now do this activity in the lab. So now we are going to observe how light refracts through a block of glass. So as you know, around the block of glass, that is on this side and this side, there is air. That is a rarer medium. Whereas the block of glass is a denser medium. And you know, when light travels from one medium to another, the path of light changes. That is what we call as refraction of light. So to do this activity, I have already drawn the outer line of the glass block, and here I have drawn the incident ray, the ray that is going to fall on the block of glass. So that has been marked here. What I am going to do now is I am going to put 2 pins on the incident ray and then find the refracted ray. So here I will put 1 pin and along the same line another pin. And then what should I do? I have to look from the other side and place the 3rd pin along the line of the incident ray and another pin along the same line. So now I have marked this is the incident ray that will refract through the glass block. Again there will be a refraction at the glass air surface, and here is the emergent ray. That is the ray that is going to come out of the block of glass. Now I can take out the block of glass. I will mark the 2 points anyway that is visible to us. Then we have to connect the 2 points so that it touches the block of glass. So I can remove the other pins as well, and when I connect the rays. Here you can see this is the incident ray. Then if I connect these 2 points, that will be the refracted ray. And here at the point where you get the interface, where the incident ray and the refracted ray touch each other, we have the normal. Again here the other normal line. So here this is the incident ray, this is the refracted ray, and that is the emergent ray. And if you observe closely, you will see that the 2 rays are parallel to each other. If I demonstrate that with a ruler, here you can see these 2 rays are parallel to each other. We can also confirm this type of refraction using a laser beam. Okay, students. So now here you can see the incident ray. It goes through the block of glass, that is the refracted ray, and again you can see the emergent ray. So by using the laser light, we can confirm that the light refracts through the block of glass. Okay, students. So you saw how to draw the diagram after refraction took place through a block of glass. The diagram I drew there was similar to this one. Only thing here, the points of the corners of the block of glass is marked as PQ, R and S, and all the rays have been marked as AB, BC, CD. But you saw a similar diagram and you saw what happens to the light ray. And when I told you all, you were able to see that these 2 rays were parallel to each other. And here you can see this is the AB is the incident ray, the ray that comes from the air medium and falls on the interface, that is the surface of the glass. And this ray, that is BC, is the refracted ray. And here you can see this is the rare medium, this is the denser medium, and the light ray refracts towards the normal. This is the angle of incidence and this is the angle of refraction. Here you can see the angle of incidence is larger than the angle of refraction. Then we have the other 2 angles. Here, this is the angle of refraction at that point where we have the glass-air interface. Here the interface is air-glass, rare medium, denser medium. Here denser medium, rare medium. Then you can see it refracts with a larger angle. So always when light travels from a rare medium into a denser medium, it refracts or bends towards the normal. But when it goes from a denser medium into a rare medium, it refracts away from the normal. That is what you can see here. So then what do we call this ray? CD. It's known as the emergent ray. Why? That is the one that is coming out of the block of glass. So when there is refraction taking place, if it is a block of glass like that, there are 2 interfaces, air glass and glass air. And these are the rays. And here you can see XY and MN are the normal lines at the point of incidence. So this is the observation that you get when we do the activity. So here, in addition to this, I can say path of light changes when it travels from from one medium to another. So then, from this activity, what can we conclude? We can conclude and say that light refracts when it travels from air to glass and from glass to air. Or in other words, it bends from its path when it travels from one medium to another medium. So that is the conclusion. Light refracts when it travels from one medium to another medium. So we can say light refracts when it travels from one medium to another medium. Now I will label all these rays and the angles in this particular diagram. So here again you can see the same diagram. It's easy for me to label all the rays and the angles from here. So here students, you can see it's the same diagram what we got from the activity. So this is PQRS, that is the block of glass. So I will start with that. PQRS is the block of glass. Block of glass. Then we have all the rays. Now you can see here A to B. What is that ray? That is the incident ray. So A, B is the incident ray. Then we have B to C. That is the ray that refracts at the air glass interface. So BC is the refracted ray. Then what do we have here? From C to D. That's the ray that comes out through the glass. We call it the emergent ray. CD is the emergent ray. And you know students, when there are ray diagrams at the point of incidence, what do we draw? We draw the normal. So here XY is a normal line. So XY is a normal or a normal line. Then after XY, what do we have? Another normal MN. So XY is when light enters from air to glass. So this is from air to glass. Then we have the other normal MN, that is also a normal line. That is when light goes from glass into air. We don't have to really specify this. This is just to show you all so that you will understand better why we draw two normal lines. Then I have told you that is the emergent ray. So here incident ray, refracted ray and the emergent ray and the normal lines have been shown. So what is the angle between the incident ray and the normal line? angle of incidence. That is given the symbol I. I is angle of incidence. Incidence. We can also call it as the incident angle. Then we have this R. That is the angle of refraction. R is the angle of refraction. Or we can call it the refracted angle. Then again we have another new symbol or a letter to denote another type of angle. That is E. So that is the angle of emergence. Why? The angle between the incident ray and the normal is the angle of incidence. Angle between the refracted ray and the normal is the angle of refraction. And angle between the emergent ray and the normal is the angle of emergence. So those are the different types of rays and angles that you will see when there is refraction of light through a block of glass. So this is again all the information that we can get from a activity where we observe the refraction of light through a block of glass. And also here you can see this ray and this ray. The incident ray and the emergent ray are parallel. The reason is air to glass and glass to air. So from here to here, light bends towards the normal. Then again from here to air, light bends away from the normal. And the angles by which they bend are also similar. Why? From air to glass and glass to air. We will see how that happens. Refraction of light from dense medium to rare medium. Now try to remember what is a dense medium? How do we classify them as dense medium and rare medium? Based on the speed of light. So if the speed is high in a certain medium, we call it the rare medium. And if the speed of light is less or slow, then we call it the dense medium. So now refraction of light from dense medium to rare medium. So what do we do first? We need to have the medium, that is the interface. So we have two mediums here. I will explain this in two ways. So let's say we need to have the dense medium and rare medium. Let's say this is glass. Glass is a denser medium than air. So then if the light is incident from there, it will refract when it enters the air medium. So to observe that, if we use a light ray, now you all know a light ray coming perpendicular to the interface travels in the same path. The same way, if the light travels along the interface also, it travels in the same direction. Only when it is incident at an angle and it enters into the other medium, it undergoes refraction. A light ray that is incident at an angle. So here what should we draw? We should draw the normal. This is the normal line. So this angle is the angle of incidence. We mark it as I. And now glass is a denser medium, air is a rarer medium. When light travels from a denser medium into a rarer medium, it refracts away from the normal. So, we will expect it to go like this, but it refracts and it refracts away from the normal. So, here the angle will be like this, larger than the angle of incidence. So, this is going to be the R, refraction angle or angle of refraction. So, this is the incident ray. This is the refracted ray. And I is the angle of incidence. And R is the angle of refraction. So, when it is going from a dense medium to a rare medium, always refracts away from the normal. So, because of that, always I is going to be smaller than R. Why? Refracts away from the normal. That is when it is travelling from a denser medium into a rarer medium. So, this is one. What if we had the two mediums the other way around? Let's say we have the glass here and air up. So, the positions of the two mediums are switched. Now, you can remember we did the activity with the glass cube. First, we had the air medium, then the glass medium, and then we had the air medium. So, both ways it's possible. But here, the light ray has to go from the dense medium to a rare medium. So, if we try to draw the ray diagram for this one, again, the ray has to incident at an angle from this medium. Why? This is the denser medium. Then what do we need to have? We need to have the normal. So, how will this refract? Like here, it has to refract away from the normal. So, here it will refract like this. So, that's going to be the refracted ray. So, here this is the incident ray. That is the refracted ray. And like we said before, angle of incidence and angle of refraction. And the values are always the angle of refraction is larger than the angle of incidence. So, remember students, what will happen when light travels from a denser medium into a rarer medium? It will refract away from the normal. Now, we will see what happens when it goes from a rarer medium into a dense medium. Refraction of light from rare medium to dense medium. So, here also I will use two diagrams. So, then we need to have the rays. Now, let's say from the rare medium to dense medium. So, I will take this as air. Air is a rare medium when compared to water. Another example. So, rarer medium, denser medium. What will happen when light travels from one medium to the other. So here we will take an incident ray that is incident with an angle at the interface. Now what will happen to this ray? It has to refract towards the normal. Why? It's going from a rare medium into a dense medium, opposite of the previous one. So it will refract towards the normal. We will have to mark the directions. This is the incident ray, that is the refracted ray. What is this angle? It is the angle of incidence, I. And what is this? It is the angle of refraction, R. So here again, I is angle of incidence and R is angle of refraction. And this is the incident ray and the refracted ray. So, what is the relationship between I and R? Here always I is going to be greater than R. Why? The light ray goes from a rare medium into a denser medium. So, it refracts towards the normal. So, if I write that down, refracts towards the normal. So, then again, if we look at the second type of rays. Now, here we will have the water medium on top and the air medium below. I am sure you know what will happen to the rays. So, why don't you all try first and then look at my diagram. So, now I will mark the two medium. This is water and this is air. So, here it has to go from the rare medium to the denser medium. So, it has to travel from air into water. I will mark the normal there. How is it going to refract? I am sure you have done it correctly. It has to refract towards the normal. So, if we mark the rays, it's going to be like this, and this is going to be the angle of incidence, and that's going to be the angle of refraction. This is the incident ray and that is the refracted ray. So, students, now you can see the angles don't change. It's always the incident angle is larger than the refracted angle. Why? Because the rays are traveling from rare medium to the denser medium. So, they always bend towards the normal. But depending on how the two media are, the ray diagram or the way we show the rays is somewhat different. So, you all have to understand that, and when you are given a question or a diagram, you have to look at the direction of the arrow and look at the positions of the two media. Then you will know why it is going this way. So, they are the same media, but the way they are, the diagrams are different. Same for the previous one as well. And remember, students, always light refracts away from the normal when going from a denser medium into a rarer medium. And it always refracts towards the normal when it going from a rare medium into a dense medium. So those are the ways in which light refracts. Now let us look at a simulation to observe how light refracts between two different mediums. Okay, students. So we will use this to understand refraction of light more better. Now here you can see I have these are the two mediums, and that is the interface there, and this is the light source. Already the normal line, I can take it off as well. Now you can see just the two media. And here the first media, that is in white color, I have selected it as air, and then we have glass. So first we will see how light rays travel from rarer medium, that is air, into a denser medium, that is glass. So to do that, I will show the way the light rays are going. If we draw the normal line, here you can see this is the angle, this is the incident ray, this is the angle of incidence, this is the refracted ray and angle of refraction. Can you all see how light ray has refracted? It has refracted towards the normal. Now let's say I told you all when it is coming along the normal, there is no refraction. It goes along the same path. The same way, if it is coming along the interface also, there is no refraction. It travels in the same path. Only when it is coming at an angle. And also you can see, students, when the angle of incidence changes, the angle of refraction is also changing. I will move it slightly to this side. Now let's say we will try to measure the angle of incidence and angle of refraction and see. So here you can see this is about, now I will bring it to a, let's say 45. If that is 45, you can see here the angle of refraction is less than 30. So I will bring this a little bit more closer. Now this is about 35, or I'll bring it to 35. You can see this is about 20. Now 30 is the angle of incidence, 20 is the angle of refraction. So now you can understand always the angle of refraction is less when light travels from a rarer medium to a denser medium. Now why does this refraction take place? Because the speed of light changes when going from one medium to another medium. So now let's say we will check the speed. Now here you can see 1.00 C. If you can remember, students, you do obviously, the speed of light in vacuum is 3 into 10 to the power of 8. What was the speed of light in air? That was also 3 into 10 to the power of 8. So it's almost the same in vacuum and air. So that is why the speed is considered as 1. Now compare to this. If I bring it to this point, here you can see it's 0.67. It's slower. So that is the reason why light rays refract. It's faster in the rare medium and it's a bit slower in the denser medium. So now you can understand why this happened. Let us look at it as a wave. Here also you can observe it more clearly. Can you see the speed here? It's a bit faster than the speed here. This is how the waves travel. Light rays are electromagnetic waves. So this is how they travel through from one medium to another medium. Now we will change the medium. Now I will off this. I will make this into glass and this into air. The opposite way. We will see how this happens. Now here you can see, I will bring it closer. There was no refraction as I switched on the bulb. I will explain that in a little while. Observe how the light ray refracts. Now here you can see this angle. Angle of incidence is small when compared to angle of refraction. So this is the denser medium, this is the rarer medium. Light ray traveling from a denser medium into rarer medium refracts away from the normal. So here also, if we bring it to the normal line that is perpendicular to the interface, there is no refraction. The same way, if we bring it to the interface, through the interface also there is no refraction. But when it comes to this point, here you can see it refracts. And the angles can be observed clearly. We'll change the media. We will change this to water. Now water is slightly less denser than glass. But still air is the rare medium, water is the denser medium. Light traveling from a denser medium into a rarer medium. So here again you can see it refracts away from the normal. So I am sure students you can understand how refraction of light takes place. Now we can have water and glass. Let's say we will select this as glass. Now can you all see what happens there? But here you can see the two angles are different. This is a little larger than this one, but the difference is less. Why? They are almost similar in density, not a huge difference. Here you can see they have given something called the index of refraction. We will discuss that after this. So they are both are somewhat closer values, similar values. That's why you don't see a big difference in the two angles. But still it's different. Going from a rarer medium into a denser medium refracts towards the normal. So here also if we move it, you can see. If we measure it also, you can observe it more clearly. A little, I will make it to 30. Here you can see it's less than 30. If I bring it to, let's say, 40, still it's less than 40. So you can see refracts towards the normal. So that is how refraction of light takes place. I am sure you can understand very clearly how this happens. Going from a rarer medium into a denser medium, light refracts towards the normal. And when it goes from a denser medium into a rarer medium, light refracts away from the normal. Okay, students. So you have understood how refraction takes place. In all these, what can you see here? Now this is the incident ray and that is the refracted ray. And this is the normal. They are all in the same plane. And also there is a ratio between the angle of incidence and angle of refraction. It is a ratio between the sine value of angle of incidence and angle of refraction. So that is a constant for two media. Now those two are known as the laws of refraction. When a light ray travels from one medium to another medium, if it bends towards the normal, the second medium is denser compared to the first medium. If the ray bends away from the normal, the second medium is rare medium compared to the first medium. So here you have to remember bends away and also it bends towards the normal. So based on that, you know to identify the two different media. And from that, we have the two laws of refraction. Now I will move on to that law. Laws of refraction. There are two laws of refraction, and the first law, the incident ray, the refracted ray, and the normal to the surface drawn at the point of incidence lie on the same plane. This is similar to reflection of light. Only difference is there the ray is reflected ray, here the ray is refracted ray. Same as before. We will look at the second law. When light refracts from one medium to another medium, the ratio of the sine of the incident angle to the sine of the refracted angle is a constant. You know the meaning of a constant. What is a constant? It has a fixed value. The value doesn't change. That depends only on the two media. So if it is between air and water, that is a fixed value. Air and glass, a fixed value. Water and glass, it will be a different value, but it will be a fixed value. This constant is called the refractive index of the second medium with respect to the first medium. Refractive index of the second medium with respect to the first medium, because the light is coming from the first medium into the second medium, or it's going from the first medium into the second medium. So always the refractive index of the second medium with respect to the first medium. And we give a special name to this law. It's called the Snell's law. The second law above is also called Snell's law. So remember students, there are two laws of refraction, though these are the two laws. The incident ray, refracted ray, and the normal to the surface drawn at the point of incidence are all in the same plane. And the ratio of the sine of the incident angle to the sine of the refracted angle is a constant, and that is known as the refractive index. It is the refractive index, and only the second law is known as the Snell's law. So if they ask you to write the laws of refraction, you have to write both. If they ask you for the Snell's law, you only write the second one. You don't write the first one. So from this, we can get an equation for the refractive index. So here, refractive index this is given the symbol n, that is equal to sine of incident angle divided by sine of refracted angle. So sine of incident angle divided by sine of refracted angle. Here we will have it as sine I over sine R. So n, that is the refractive index is equal to sin I over sin R. So this is a constant for different media. Now let's say if one media is air and the other one is water. Light ray travels from air into water. So this is I, this is R. So when you write the refractive index, we have to say from what medium to what medium. So it's going from air into water. Refractive index of water with respect to air. Refractive index of the second medium, that is water, with respect to the first medium, that is air. So this is how we denote from where to where the light is traveling. So if it was from air to glass, you have to say A-N-G, G for glass there. Or if it's from water to glass, W here, then N and G. So that is how we denote the different types of refractive index. And these are the laws of refraction. For a light ray that travels from air to glass, the refractive index is, so as I told you, refractive index, it's going from air to glass. So we have to write A, N, G. And that is going to be sin I over sin R. Sin I is going to be in what medium? In the air medium. Whereas sin R is going to be in the glass medium. So from air to glass. For rays that enter from glass to air, the refractive index is going to be glass in air. So that is also going to be sin I over sin R. Now let's say we take like this. Let's say this is air, this is glass. I will put this as angle X and this as angle Y. Now here, I haven't shown the direction. Here, it's going from air to glass. So what is going to be I? It's going to be sin X over sin Y. The same thing. Here, what is happening? The light is going from glass to air. So here what is going to happen? Sin Y over sin X. Now can you see the relationship? Now this is a reciprocal of this value. So that means this refractive index, where light travels from glass to air, will be a reciprocal value of the refractive index from air to glass. Because it's the same two media, when light travels from one to the other, because of the density difference, the refractive index also becomes reciprocal. But the angles are going to be the same. That is, here the X and Y will not change. But depending on from where to where the light is traveling, we have to substitute the values in a different way. That is why we have to specify from what medium to what medium. Refractive index of water relative to air. So here you can see air to water 1.33 and refractive index of glass relative to air from air to glass, that is 1.5. Now, if you can remember students, when we were watching the simulation, you were able to see these two values. I told you all I will explain that in a while. Now you know what that value is. So this is a fixed value for two different media. And now you can understand. We have discussed allotropes of carbon. I have mentioned this before. Diamond is one allotrope of carbon. We saw the refractive angle. And I told you all, diamond has a very high refractive index. That is why it gives that glittery and colorful shine. So there, due to refraction of light, light separates into colors. That is why you get that glitter from diamond with the different colors. So that's why it's very valuable as well. So this is how we denote refractive index. Now let's say we are looking at different media, from air to water, water to air, air to glass, glass to air. Like that we can change the media. But you all know, we know the speed of light in vacuum. So normally that is the standard speed. That is the highest speed of light. So if we are to consider the refractive index between vacuum and a medium, then that will be the refractive index related to that particular medium. The refractive index defined above is the refractive index of one medium relative to another medium. So here it is one medium relative to another medium. Therefore, it depends on both media. If we use a vacuum, so note this, if we use a vacuum instead of the first media, that is, if we consider a light ray entering from a vacuum to some medium, then the refractive index depends only on one medium. Then it depends only on one medium. And this is normally referred to as the refractive index of that medium. So here you can see this is the refractive index of that particular medium. So here what are we doing? We take one medium as the vacuum. This is the vacuum, and let's say this is glass. So when light travels from vacuum into glass, how is it going to refract? It's going to refract towards the normal. So it will refract towards the normal. Then we have the sin I value and sin R values. This is the angle of incident because this is the incident ray, and that is the angle of refraction. So when you calculate the refractive index, here it's going to be vacuum to glass. This can be written as the refractive index of glass. We don't have to show that this is the vacuum. We can directly write only the glass. The same way, if it's going to travel from vacuum into water, then we will write the refractive index of water as NW. We are specifying only the second medium. We don't have to specify the first medium. This is theoretically possible. But is it possible to do that in the lab? Or practically, is it possible to always get the vacuum and a medium? No, because the vacuum is actually above or outer than our atmosphere. So when light comes from the sun towards the earth, it travels through vacuum. But as it enters the atmosphere, it's traveling through air. You can remember, students, the speed of light in vacuum and air are equal. Both are 3 into 10 to the power of 8 meters per second. So therefore, since it's difficult to use a vacuum as the first medium, we use air as the first medium, and when we calculate the refractive index, we consider that as the refractive index of that medium. Although it has to be relative to vacuum, as here, even if it goes from air into a particular medium, that is from air to glass here, still we take the refractive index as the refractive index of that medium, because the speed of light in vacuum and air are the same. So that is the next one. Refractive index of water is the ratio of the sine of the incident angle to the sine of the refracted angle when a light ray travels from vacuum to water. Because the velocity of light in air is only slightly different from that in a vacuum, and because it is practically difficult to make measurements of refractive index relative to a vacuum, often the refractive index of a medium relative to air is used as the refractive index of that medium. This is what I explained before. There are no units for the refractive index of refraction. So here you have to remember, students, often the refractive index of a medium relative to air is used as the refractive index of that medium. So instead of writing it as ANG, you can also write it as NG. Because here it should have been vacuum, but even the air being the first medium, we consider the values as equal. Why? There is only slightly different. The speed of light in vacuum and speed of light in air are slightly different. But when we take the approximate value, you have seen both the speeds are given as 3 into 10 to the power of 8 meters per second. So this is how we write the refractive index. So now you can see there are no units for the index. Why no units? There are no units for the index of refraction. Why is that? When we calculate, let's say from air to glass, what do we do here? We use the sine I over sine R. What is sine I? Angle of incidence. What is sine R? Angle of refraction. So here sine values don't have a unit. And also we are dividing sine by sine. So anyway they don't have a unit. And also when we divide one by the other, there is no unit. So that is why there are no units for the index of refraction. This is a comparison ratio. Ratio does not have a unit. So that is how we denote the refractive index for different mediums. Either in relation to another medium or relative to the vacuum or relative to air. So relative to vacuum is considered as the refractive index of that particular medium, but practically it's difficult to measure it and calculate it, and also the speed of light in air and vacuum are almost the same. So, therefore, we consider the refractive index relative to air as the refractive index of that medium. And refractive index does not have a unit. So, that is refraction of light from one medium to another. Now, we will look at another concept related to this refraction of light. Total internal reflection and critical angle. A light ray travelling from water to air. How are their densities? Which is the denser medium? Which is the rarer medium? Water is the denser medium and air is the rare medium or rarer medium. So, how is light going to bend here? It's coming from the denser medium into the rarer medium. So, it has to refract away from the normal. So, we will look at this refraction. So, we will take the interface of the two media, a ray that is going to come from water. This is the normal at the point of incidence and this is going to refract away from the normal. So, here it's going to go away from the normal. This is the refracted ray. So, this is going to be air and this is water. And this is the angle of incidence, this is the angle of refraction. You know always the angle of refraction is greater than angle of incidence. Why? This is the denser medium and that is the rarer medium. And I have shown you all this before. You can have the medium the other way around. You can have the water here and air there. Then the light ray has to travel from here into the air medium. The main thing is it has to travel from water into air. Now, this is a certain angle of incidence and the respective angle of refraction. Let's say we increase the angle of incidence. Then what will happen? Now, when I increase the angle of incidence a little bit more, let's say something like this. So, then the light has to refract with a even more higher refractive angle. So, here we have to show the direction of the two rays. This is the incident ray, this is the refracted ray. So, here you can see this is the angle of incidence, this is angle of refraction. I will, to differentiate, I will write it as I1 R1 and I2 R2. You can see I1 is less than I2. So, therefore, R1 is also less than R2. Or in other words, you can say when we increase the angle of incidence, the angle of refraction also increases. If we keep on increasing it that way, the angle of refraction will also increase. Then what will happen? We will look at another instance. Now here, the light ray comes like this. Even a right. So, at this point, this is the angle of incidence. Now, I'll take it as I3. Then what will happen is, it is even more larger than the first two angles. There is no space for the angle of refraction. The refracted ray will go through this interface. That is, the angle will be 90 degrees. So, at the point where the angle of refraction is 90 degrees, the angle of incidence is called the critical angle. So, when light rays travel from a denser medium into a rarer medium, you keep on increasing the angle of incidence, the angle of refraction increases, and at one point, the angle of refraction becomes 90 degrees. At that point, the refracted ray travels through the interface between the two media. And then we call the angle of incidence as critical angle. So, this is what is called the critical angle. And this critical angle is a fixed value for a certain medium. The critical angle of glass is a fixed value. Critical angle of water is a fixed value. That is with respect to another rarer medium. After this point, now let's say what happens if we increase the angle furthermore. So then what will happen is, now we have the interface and this is the normal. I have a ray like this. Now this is greater than critical angle. So here I greater than critical angle. And critical angle is denoted by the letter C. Then what will happen? The light ray will not refract, it will reflect within the denser medium. So here the light ray will reflect within the denser medium. So this point we call it the total internal reflection. Why? It's reflecting and it is reflecting within the denser medium. So therefore it's known as total internal reflection. So this is where total internal reflection takes place. So we will go through the diagrams again. We have a small angle of incidence. Accordingly, there is a greater angle of refraction. Why? From a denser medium to a rarer medium. We increase the angle of incidence. Accordingly, the angle of refraction increases. And at one point, when there is a high angle of incidence, the light ray refracts through the interface. And at that point, the angle of refraction is 90 degrees. This is equal to angle of refraction. And then we call the angle of incidence as the critical angle. And thereafter, if we increase the angle of incidence, this is I4, that is greater than critical angle, then there will be no refraction. Instead, the light will reflect within the same denser medium. Remember that, students. This will happen only when light travels from a denser medium into a rarer medium. So, after that point, it's going to be total internal reflection. So, if we increase the ray further, angle of incidence further, that will be also total internal reflection. So, any angle greater than the critical angle, there will be no refraction, there will be only total internal reflection. So, this is the concept of total internal reflection. Again, I will show you all that using the simulation. Okay, students. So, you are familiar with this. We have the two media, air and glass. Now what is the rare medium? Air. So the glass is the denser medium. We will see whether total internal reflection will take place here. So to do that, I have the light source. You can see angle of incidence, angle of refraction, and how the light rays are going to refract. Now we will increase the angle of incidence. You can see accordingly, I will show you the angles as well. The angle of refraction is increasing, but here the light ray bends towards the normal. So then, even if we keep on increasing the angle, still it is refracting. So if we increase it further, it will come to the point where it's traveling through the interface. There is no total internal reflection when light travels from a rare medium into a denser medium. So now I will bring it to a point where we have the glass here, that is the denser medium, and air there. Now you can see what happens. It's traveling in the same path. When I increase the angle of incidence, you can see accordingly the angle of refraction is increasing, and also light bends away from the normal. So it's still refraction. We keep on increasing the angle. Now you can see still the angle has increased. Now it's 41.5 and here it's 83.4. Up to 42 we can increase. Why? 42 degrees is the critical angle of glass. So you can see if I increase it after it's greater than 42, there will be no refraction, but there will be total internal reflection. Here you can observe that. When I have it 41.3, when I take it here 41 up to 41.9, then it starts total internal reflection. So this is how total internal reflection works. So here 42 is the critical angle of glass. If we change this to water, here you can see still it is refracting. Why? The critical angle of water is higher than this. So here when I increase it further up to 49, then only there is total internal reflection above 49. So you can see it's a total internal reflection. So remember students, when light travels from a denser medium into a rarer medium, there will be total internal reflection. And the critical angle is fixed for a certain medium. Glass, it's 42 degrees and water, it's 49 degrees. So after that point only, there will be total internal reflection. So students, now you know what total internal reflection is, and you know that the critical angle varies from medium to medium. So we have a table here with the material and the critical angle. As I told you, water has a critical angle of 49 degrees. Glass has a critical angle of 42 degrees, whereas diamond has a very small critical angle of 24 degrees. So above these critical angle, if you increase the angle of incidence, there will be only total internal reflection. And always remember, total internal reflection can take place only when light travels from a denser medium to a rare medium, not the other way around. So that is total internal reflection. Now we will move on to the next one, the applications of total internal reflection. So we saw what total internal reflection is, and now the applications. The first application is the optical fiber. Here what is shown to you is an endoscope. It is an instrument used to carry out the endoscopy technology. Endoscopy is a technology used in the field of medicine. They use this to observe internal organs, the surfaces of internal organs, and even to perform minor surgeries. So, if you need a small, very minor surgery, you don't have to cut open any part of the body. Instead, they can use this endoscope instrument. Now, in this endoscope, there is a tube inserted into the body either through the mouth or the anus, one of the natural body openings. And that is directed to the part where the surgery has to be performed or where the organ has to be observed. And from this set, the doctor or the surgeon can observe what is happening there. And from here, you can see light enters into the instrument, that is the endoscope. And all these parts are made up of optical fibers. That is this, the first application. This is optical fiber. And within the optical fiber, if this is the optical fiber, if light is sent in one direction at an angle, it will only undergo total internal reflection like this. It will not refract or it will not come out of the tube. Throughout the tube, there will be total internal reflection. That is what happens within the optical fiber. So, light is given from here. Light reaches the organ and there they can observe the organ clearly because there is lot of light falling on the part of the organ, and the doctor can observe from this side. Or otherwise, what he can do is by observing it, he can also perform surgeries. When they need to perform surgeries, the tube will be a little bit more complex. They will have other tubes through which the tiny instruments are also inserted into the body. So, there the surgery can be performed. So, this is a very advanced technique that is very useful in the field of medicine. So, that is optical fibers. So, that is used in endoscope, the instrument which is used for endoscopy. The same optical fiber is used here as well. It is used in telephone and communication, in internet connections. So, this is another application of optical fibers. They are used in telephone communication and internet connections. The reason is, even if they are kilometers in length, very long fibers, still the waves will not be lost. Why? There is only total internal reflection taking place. So, the signals of this telephone communication and internet connection can travel faster and over a longer distance without being lost. So, because of that, they are very useful in this as well. So, optical fibers can be used in endoscopes as well as for telephone communication and internet connection. In addition to that, there is another application. These optical fibers are used to make ornaments. You might have seen ornaments like this where there is a structure like this, a vessel with all the optical fibers coming out of the vessel. And these optical fibers have a certain glow. They have a light, they emit light, and at the ends also they have a glow. And time to time the color of the glow will change, and it is a very attractive ornament. To make these ornaments also, they can use optical fibers. These same ornaments, since they have a colorful glow and they are not harmful because there is no flame involved, but still you see a light and it's very colorful, it's very attractive. The same type of ornaments in the shape of a rod or in different shapes can be used in stage performances to generate different types of light, so that it becomes more attractive. So, the optical fibers can also be used in stage performances. So, those are the applications of total internal reflection, and that also optical fibers. Another application of total internal reflection, that is the total internal reflection by prisms. So, here you can see this is a prism. Now, if you just look at it as a triangle, what is this angle? It is a 90 degrees angle. So, if this is a prism with a 90 degrees angle, these two angles will be 45 degrees. So, a prism with one angle 90 degrees and the other two angles 45 degrees each can be used to produce total internal reflection. So, we can use this prism to produce total internal reflection. Such prisms are used in cameras, telescopes and binoculars. So, in all three devices or the instruments, they use this type of prisms in order to achieve total internal reflection of light. The critical angle of glass is 42 degrees. We have discussed this before. Therefore, if the incident angle inside glass is greater than 42 degrees, the light ray will undergo total internal reflection. So, normally students, you can see in most of the glasses, the critical angle is 42 degrees. So, here also we take the value as 42 degrees. We had it in the table before. The critical angle of glass is 42. So, therefore, if we send light that is incident with an angle greater than 42 degrees. So, if the angle inside glass is greater than 42 degrees, the light ray will undergo reflection. So, let's say we will take a light ray that is going like this. Now, this light ray is perpendicular to this first surface. To the surface of the prism, it is incident at 90 degrees angle. So, that means it's going through the normal line. So, any ray that is going perpendicular to the surface or going through the normal line will travel in the same path. So, there will be no refraction there. But when it reaches this point, here if we take the angle, this angle will be, if we take this angle, it is greater than 43 degrees. So, this particular angle is going to be greater than 42 degrees. So, that means there is going to be total internal reflection, not refraction. So, it will refract like this. So, here the ray will reflect like this. So the ray that is entering the prism from one face or one surface, it does not undergo refraction or reflection, it just travels in the same path, and at this point it is incident with an angle greater than 42 degrees, which is the critical angle of glass. So therefore it reflects. So when it reflects, again it reaches the other surface. Here also it falls with a 90 degrees angle. So again through the normal line. Therefore it doesn't refract. So here you can see the angle of light has been turned by 90 degrees. So the light that comes this way is coming out from the other end. A light ray entering one face of a prism perpendicular to the surface, this ray is not refracted at the surface. So that is this. Next, if falls on the second face of the prism with an incident angle of 45 degrees, so that is greater than 42 degrees. Because this incident angle is greater than the critical angle in glass, the light ray undergoes total internal reflection and travels perpendicular to the third face, that is this, of the prism. The ray emerges from this face without bending. So here again it doesn't bend. This technique allows us to bend the light ray by an angle of 90 degrees. That is what happens here. So here we bend the light ray by 90 degrees. So that you can see the ray that is going this way bends with an angle of 90 degrees. So this is the incident ray. This is the ray that is emerging out of the prism. So because of the total internal reflection, it comes out like that. So this technique is useful in 3 optical instruments: the camera, telescope and binoculars. You all know the functions of all these. Cameras are used to take photographs. Telescopes are used to observe far away objects in a larger manner, enlarged manner and closer, and also even binoculars. They are also used to observe far away objects close and in an enlarged manner, but the difference is binoculars we use both eyes, and telescope you have to observe only with one eye, and also the way the image forms is different in these 2 optical instruments. But in all 3 they use this type of prism in order to bend light or bend the light ray by an angle of 90 degrees. So those are the applications of total internal reflection. You saw how it is used in optical fibers and also in a prism. Prisms are again used in these optical devices. So with that, students, we have come to the end of discussion on refraction as well as total internal reflection. Now I will discuss a question with you all. The exercise given in your textbook. 5.1 exercise. The figure shows a man holding a fishing rod that you can see here. The man is holding a fishing rod and there are fishes there. The fish appears to the man at a slightly higher position. What is the reason for this? So here if you look at the picture, this is the real fish. But this is where he sees it, slightly higher position. What is the reason? The reason is light that comes from the fish refracts at the water-air interface. So that is the reason. So if we write the reason for the first question, it is because light coming from the fish through water refracts at the water air interface. So that is the reason. You can also write as a very short answer. You can say refraction of light. That is also correct. The next question. Draw a ray diagram to show how the position appears to be raised. We have drawn a similar ray diagram. You all can remember at the beginning of the lesson, we observed an object, a coin that is inside water being slightly raised. So, you know how to draw ray diagram for that. So, I am sure you will draw it first and then you will look at my ray diagram to confirm that you have done it correctly. So, now I will draw the ray diagram for you all. So, it is for the second question. What do we have? We have the water-air interface like that. And this is going to be water and this is air. Always students, you have to label the two media. Then only we will know why the light rays are bending in such a manner. So, if we have the fish here, there will be a light ray going from the fish to this point. The normal line is going to be here. So, the ray is coming from a denser medium. Water is a denser medium, air is a rare medium. So, what will happen there? It will refract away from the normal. So, the refraction will be something like this. If we mark the rays, this is the incident ray, this is the refracted ray. Is this enough to get the image? No. You need two rays. So, we have to draw another ray starting from the same point but incident at a different point. So, here we have the normal. Again, that also refracts away from the normal. So, that is the second incident ray. Now, what do? We use broken lines to draw the rays longer or to extrapolate the rays. So, if we extrapolate this and this ray, you will see the fish as being somewhere here. So, if we draw with, now this is a diagrammatic representation students, I didn't measure any of the angles. When we measure the angles and draw a very proper ray diagram, you will exactly get the rays at the correct point. So, here this is just a diagram to show what happens and the person is going to observe from here. The fisherman or the person is there and this is the apparent depth, the depth that appears to us, and what is this? Full depth, that is the real depth. Apparent depth and real depth. So, students, this is the ray diagram that you will get when we see the fish slightly above from the position. So, if we answer the questions, why it looks as if it's slightly raised? It is because light coming from the fish through water refracts at the water-air interface. It has to be interface. So, this is the interface and it refracts at this point. And if they ask you to draw the ray diagram, this is how you have to show it. You have to use two sets of rays so that you can get the position of the image. And also, when you draw ray diagrams, you have to use very thin pencils, a ruler, and also if you draw it correctly according to the angles, then you will get the image at the exact point. So, here I drew the diagram without measuring the angles. So, it is a rough diagram of how light refracts. And this is what you are supposed to show. And you know to explain what apparent depth and real depth are. So, with that, students, I come to the end of discussion on this topic, that is refraction of light and total internal reflection and their uses or applications. So far we have discussed reflection of light by plane mirrors and curved mirrors and also refraction of light. After this, we will be discussing a different topic but related to optics, the refraction of light by lenses and the images formed by the lenses.